Welcome to Ready to Derive. In this video, we'll be exploring properties of integrals. It's a dry subject at times, but I try to make it interesting with some sort of real-world examples and also lots of pretty illustrations and demonstrations. The only notation or concept you have to be familiar with is this. So that is the definite integral of f of x from a to b with respect to x. What does that represent? You need to know that that is the area enclosed between f of x and the x-axis over the interval a to b. And visually, what does that look like? If we could work out the answer to that definite integral, it would give us the exact area that's shaded in blue. We're not at that point yet. We are going to be working mostly with shapes that are rectangular, triangular, so that we can work out exact areas. But for the time being, this is all you need to know. So without further ado, let's get started. We will begin by demonstrating why the sign of a definite integral can be positive or negative and why that makes sense. So even though definite integrals indicate area, and area is usually positive, it's possible for the answer of a definite integral to be negative. So here's a scenario that we treated in the first video in this unit on area and accumulation. This is a velocity curve. We could call it, let's just give it a name, v of t. And we might be interested in what is the definite integral of v from 0 to 6, which we understand to be the area of that portion of the blue region. So the area, the base is 6, the height is 60, and so the area of a triangle is half base times height. Now notice that the unit along the x-axis is time, seconds. So I'm going to keep the units in play because they'll help us to understand the units of the answer. So 60 meters per second. And as you can see, the seconds cancel and we are left with 180 meters. So what does that mean? What is happening to the ball over that interval 0 to 6? And what you need to interpret this is that at t equals 6 seconds, the object is 180 meters above. Above because the answer is positive. So above its height at t equals 0 seconds. So the ball has accumulated height. So what happens between 6 and 10? Well, we see the velocity curve is now negative. And in the negative region, which means that the ball is reversing direction. It's falling back down to the ground. So the base here is 4. And what we are going to be careful about here is that the velocity, the y value there, is technically negative 40. Let's work with that. So a half times 4 times negative 40 is negative 80. And we know from before that the units are meters. So here we have an example of a definite integral taking on a negative number because of what it means. Okay, so it means that at t equals 10 seconds, the object is now 80 meters below its height at t equals 6 seconds. So it makes sense for the answer to be negative because otherwise how do we know if we're in the process of accumulating height or deaccumulating height, as the case is with this object. So one last thing we might think about is, so what would be the area from 0 to 10? Now, it's probably intuitive to you that you would just do, it gained 180 meters, it lost 80 meters, and so now maybe this answer should be 100 meters, and that is correct. At t equals 10 seconds, the object ends up being 100 meters above its height at t equals 0 seconds, so it gained 180, it lost 80, it's still 100 meters above its original height. This particular result about sort of combining areas under the curve, we will formalize in a later slide. Now we'll look at what it means to integrate backwards. Called this the integrating backwards property. It's not really the formal name, but it's just a good way to remember it. So what we're going to do is consider what happens if we reverse the upper and lower limits of the integrand, of the definite integral. So now what does it mean to integrate from 6 to 0? And what I want you to think about, it's really the concept of kind of undoing time and finding out what happened, in this case, 6 seconds before t equals 6. So what you have to understand is between 0 and 6, it gained 180 meters, as we discovered in the slide before. So at t equals 6, it's 180 meters above where it was at 0. So if we want to go back to 0, it now is going to be 180 meters below where it was at t equals 6. So this concept of undoing time might help you to understand this important relationship. Obviously, if you reverse, go from 6 to 0, it's going to be the opposite answer from whatever the integral would have been from 0 to 6. So in the same way, okay, and there it just formalizes. So at t equals 0, the object is now 180 meters below where it was at t equals 6. And in the same way, if you think about this, so what if we undo time? If we come back from 10 seconds to 6 seconds, not surprisingly, it would be, this will be 80. So even though the green area technically is negative, if you go from 6 to 10, reversing that, going from 10 to 6, it's the opposite. So the double negative makes a positive. And so that leads us, and just to interpret that, so at t equals 6, the object is 80 meters above its height at t equals 10. So like I said, undoing time is a nice way to think about it. So let's just formalize this here. So if we want the integral from b to a, so from b to a, it will be the opposite of whatever the area is from a to b. So let's just practice the last couple of properties now, just to make sure we have it under our belt. So the definite integral of 0 from 0 to 2 of f of x would be this area here. And we see that the base is 2, so we can do 1/2 times 2. And we can see that the height is 4 times 4, and that the answer comes out to be 4 square units. All right, let's try this from 2 to 4. So just to change colors, let's see, we're underneath now, underneath the x-axis. So we know that's going to be negative. This is a semicircle, and the radius is 1. So the area should be 1/2 times pi r squared, 1 squared. And let's not just forget, though, it is going to be a negative answer because it's below the x-axis, that area. So the answer is negative pi over 2. And now to change it up a little, now we want the integral from 6 to 4. Well, I much prefer to go for the lower limit to be the lower number. So I'm going to immediately change that to this. So negative the integral from 4 to 6, as we saw from the previous property. And let's see, the area under this triangle, so that the area of that triangle is 0.5. The area of that square is 1. So this is going to be negative 1.5 because we are reversing the order. So obvious question that's begging is what would be the area from 0 to 6? We've already hinted at this, and we're going to formalize this in the next slide. So let's consider that same function from before, and we're interested in the area under the curve from 0 to 6. And hopefully it makes intuitive sense that we would just find the area from 0 to 2, then 2 to 4, and then 4 to 6. And the area under the curve from 0 to 2 is just that green triangle, so that would be 4. From 2 to 4, it's the purple region, which we know is below the x-axis, so it's negative pi over 2. And then 4 to 6 is the orange region. So that would make 5.5 minus pi over 2. And that sort of makes intuitive sense, I hope. So we can formalize that. Now, in this case, we wrote it in terms of 3 integrals. The more simple formulation is just in terms of 2 integrals, but you can keep splitting those integrals up in the same way using this interval addition property. Now, let's take a look at this sort of more generally, because this makes sense. When C is between A and B, it sort of makes sense that if you want the area from A to B, so if you want the area all the way from A to B, you'd find the area from A to C, and that add up the area from C to B. So it seems to make intuitive sense when C is between those. But what happens in the case where C is beyond B? Because now, if we want the area from A to B, we still only want this region, but somehow it's telling us to take the area from A to C. So let me just think of the yellow and green combined, take that area and then add on another area from C to B. Well, what is the area from C to B? So let's have a look at that. From C to B would look like this, C to B. Now notice, because B is before C, this is one of those reverse integration issues. So we want to use that property from before, because we like B to be less than C, so the lower limit to be less than the upper limit. So as it turns out, we would end up subtracting out. Okay, so because the area from C to B is the opposite from B to C, we would end up actually subtracting out this green area and then get left with the area that we were interested in, which is from A to B. So this formula works no matter where C is located. The formula is always true. So here's another property which intuitively also makes sense. It's called the linearity property because, well, we've seen it before, and it's kind of the way you'd expect functions to behave. So the integral of the sum or difference of two functions is just the sum or difference, respectively, of those integrals, of the individual integrals of the functions. So this makes sense also because, remember, the definite integral is the limit of a Riemann sum. And if we recall, limits share this linearity property. The limit of the sum of two functions is just the sum of the two limits of the individual functions. So it makes sense, but it might be nice to see it visually. So imagine this was f of x. Then we're interested in the area from 0 to 2. And we would like to, and then here's g of x. And how is it possible? So now if we look at f plus g, the function f plus g, so the red function added with the green function would actually make the purple function. And if we're interested in summing them, so that purple area there, this purple area over here represents the definite integral of the sum of the two functions. And how is that achieved? How is it possible that that purple area is the sum of the green and the red areas? Well, it turns out that the green area would just be the area of this triangle here. All right. And if we then just add on, it turns out that if we want to add on that red bit, I know it looks distorted, but if we added on, say, all the vertical line segments along here and sort of stack them up as we're going along, it turns out that those two, that this shaded red area and this, are exactly the same. So this is a property that gets used a lot without really even thinking that we're using it. But it's important to establish it and give it a proper name. So now we will look at the second linearity property, which says that if you take a function and, perform a vertical stretch on it, what will happen to the definite integral, the area under the curve? So if you can see here, the red in the function in the red is f of x, and in green I've just graphed 1.5 times f of x, and I'm going to see what the effect is on the area under that curve on that vertical transformation. So if we look at the area from 0 to 5, so this area, let's see, is a triangle. Half 4 times 4 equals 8, and here's a triangle whose base is 1, height is 2, and that's 1. Of course, that's negative because it's under the x-axis, but that's okay. We just do 8 minus 1 and we get 7. Now, let's do it now for the green one. So for the green figure, notice that the base stays the same. It's still 4, but the height is now 6 because that's 1.5 times the original height. And that works out to be, let's see, 12. And then under here we have half, base is 1 still. The height is now 3, and that becomes 1.5. So the area, the green region area, is 10.5. And then what we need to notice is how does this compare to this? Well, turns that out that 12 is 1.5 times 8. 1.5 is 1.5 times 1, and 7 times 1.5, not surprisingly, is 10.5. So what this summarizes to is that if we carry out a vertical stretch on a function, so multiply that function by c, we can actually just extract the c from that definite integral, and the result will be c times the area under the untransformed graph. So 2 more properties of integration, and then we are done and can practice a little. So here's the integral of a constant. So if we think that this is really f of x, it's just f of x is equal to some constant number. So what would that look like? Well, it would be a constant function, f of x, and it equals c. So if we want the area under that constant function, so from a to b, we can see that we have a rectangle whose height is c and whose base is the difference between b and a, so b minus a. So the answer to the integral of a constant is just c times whatever the constant is times the distance b minus a. And the last one is the integral at a point property. So if we want the integral of a function, any function from a to a, so what would that look like? From a to a would be, all right, here's a function, and we are interested in the integral from here to where? To there again. So the integral, with the area, there is no area there, it's just a line. So in fact, and if you think about it, there's no accumulation because we're not going from a to b, so this function cannot possibly accumulate anything, and so the answer to this is 0. So now let's do a practice problem, putting all these properties together. So the first one we'll do is we will work out the integral from -1 to 2 of this quantity. Now I look here and I already see that 5, the constant, times the function, and I know from a property before that I can just factor that 5 out, -1 to 2 of f of x. And also because I have a sum of 2 functions here, I think I will separate them out as well for convenience. So separate those out to this situation. And then we have 5 times, well, the integral, this integral here from -1 to 2 of f of x dx is up here. It's 3, so I'll put 3 there. Plus, and now we have the integral of the definite integral of a constant. And we know that that constant has to be multiplied by the difference of the upper and lower limits, 2 minus -1. And so if you work that all out, 5 times 3 is 15, plus 12, and the answer is 27. All right, next one. So now we have the definite integral of a difference, and we know that we can separate those out like this, to 9 of g of x dx, and the integral from -1 to 9 of f of x dx is 10 minus, and for g it's -2, 10 minus -2 is 12. Okay, how about the next one? So the integral from 2 to 9 of f of x. Now notice that, I'll just use a different color for contrast, we have the 2 there and the 9 there, but somehow we need to get -1 involved. So we are just going to use that interval addition property, and we know that it doesn't matter where -1 sits in relation to these, we can always, in relation to 2 and 9, we can always split that integral from 2 to 9. We can go from 2 to -1 and then from -1 to 9. And now, if we look up here, up to this one here, we see we have the integral from -1 to 2. So we're going to take one more step and use the property where we reverse the order of integration. So this will be negative the integral from 1 to 2 of f of x dx, and this can stay the same, f of x dx. And so the first one is negative 3 plus 10, and the answer is 7. And finally, the integral from 2 to 2, the integral at a point is 0. So for our last practice problem, we're going to try and condense the three integrals seen here, definite integrals, into one definite integral using this property. And the most important thing to see here is that in order to use this property, that the c has to be the upper limit of the first integral and the lower limit of the second that are being added together, and then you can condense that and get rid of the c. So we can see that here. We can see that we have a 3 as an upper limit, 3 is a lower limit. So this can be condensed negative 2 to 4. Now the other thing we see is that this is a plus here, and it doesn't look like minuses are permitted. So we're going to reverse the order of integration so we can make that plus and go from 0 to negative 2. Now we do see negative 2, but now it's sort of not in the same orientation. It seems that negative 2 is lower limit there and the upper limit there. But if you just switch, literally just exchange them. So let's put 0 to negative 2 first, and then negative 2 to 4 afterwards. Then we see that we have these matching. And finally, we can condense to 0 to 4 the definite integral of f of t dt. And that's it. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.